quiz do. Let's go ahead and turn that in. Looking at integrating rational functions. So recall that a rational function is of the form of a polynomial divided by a polynomial. Also recall that it's said to be proper when the degree of the numerator is smaller than the degree of the denominator. Favorite quiz? When integrating a rational function, the first thing you want to do, make sure it's proper. If it's not, make it proper. How do you do that? So glad you asked. Division. Either synthetic, which is very unlikely, or polynomial long division, which is way more likely. Next, you completely factor your term. Two types of factors. Linear factor, x minus a, or irreducible quadratic, ax squared plus bx plus c, meaning it has no real solutions, has no real zeros. Those are the two types. Factors can be repeated. So you actually have 4 scenarios to deal with. If x minus a is a factor, that contributes one term to the decomposition. Capital A over x minus a, where this capital A is a constant that needs to be found. If that linear factor is being raised to a power, let's call it r. Then it's going to contribute that entire sum to the decomposition. where again, each of the a sub i's is a constant that needs to be found. You have a quadratic factor. There's its contribution to the partial fraction decomposition. And if it's repeated, then it adds, again, an entire sum to the decomposition. You sum up all of your contributions. E of x over q of x is equal to that. Multiply both sides by q of x. And then you can solve for your constants. Depending on the problem, solving for the constants can be really dangerous. Ultimately, you wind up with a system of linear equations. And they suck. So if you get a complicated system, I'm just going to show you how to do it on that side. And if you've taken linear algebra, then you also know how you can solve it by setting solutions. You're still going to have to rewrite that again. I'm just going to call it I. So we're trying to find I. Step one, make sure it's proper. Is it proper? Nope. Nope. So we have to go back to pre-calculus and do polynomial division. X to the fourth divided by x cubed is what?
X.
Multiply this by x. Subtract. Remember, these are all going to be zeros afterwards. Oh, look at that. They drop out. Is that degree smaller than that degree?
The one on the bottom?
Yes. This degree is smaller than this.
Yeah.
Then you're done, that's your remainder. So now, our antiderivative becomes x minus the quantity of x plus 1 over x cubed minus x squared dx. This is now proper.
Let's see. Did we do anything to that remainder?
What do you mean do anything?
Because we have negative x minus 1. Do we distribute like a negative?
Yeah, factor the minus out.
Oh, okay. So normally it would be x plus if that was like that.
Well, it's always going to be plus the remainder over.
Okay.
But because this had a negative comment, I just factored out the negative or minus.
Okay.
Well, that antiderivative is simple. That's rational. And we can't even simplify that. And if this is a monomial in the denominator, technically it's rational, but it's easy to do without partial fraction. If there are factors you can cancel, you want to do that. Of this, there's nothing you can do. So we're going to have to go and write its partial fraction decomposition. Completely factor the denominator. How does the denominator factor?
It should be x squared and then x minus 1.
How you write the terms, the order in which you write the terms does not matter. I'll start with this x squared factor. Is that linear or irreducible quadratic? X squared linear or irreducible quadratic? You say quadratic? You're not technically incorrect. If I write it that way. For purposes of partial fraction decomposition, x squared is linear. It's repeated, it has a repeated root. So it contributes two terms. A over x plus b over x squared. That takes care of x squared. X minus 1 is linear. It'll contribute c over x minus 1. This is the form of our decomposition. We now have to solve for a, b, and c. So multiply through by the denominator, x squared times x minus 1. That's what you should be left with. Now, at this point, there are two ways to proceed. The first way is by gathering like terms. The second way is substitution, let's call it. This has to be true for every value of x. So set x equal to 1. That becomes 0. That becomes 0. We're left with c on the right-hand side. Left-hand side, we're left with 2. C has to be 2.
So we should not try to actually distribute those out.
You can, and I'm going to do that.
Okay.
So that's typically the method I'll go to, because when you get down to irreducible quadratic, that's typically the easiest way to do it.
Okay.
Why did I say x equals 0? That should be x equals 1. X equals 0. That term becomes 0. This term becomes 0. This is negative b. Right? So right-hand side we get negative b. Left-hand side we get 1. So b has to be negative 1. That leaves us with a problem. We can't isolate a. But again, it has to be true for every single value of x. So take a value of x other than 1 and 0.
2.
Right-hand side becomes 3, right? This will be 2a.
Yeah. Times 1, wouldn't it?
Minus, right, because b is negative 1.
Which means plus 1.
So minus 2. I'm saying minus because this is already plus.
Oh, okay.
And then 3 minus, or I'm sorry, not 2. I mean, x is 3. Minus 1, right? 2 minus 1 is 1.
Mm-hmm.
Plus, c is 2. 2 times 2 squared is 8. Solve for a. Seven. So 3 minus 7 is negative 4. Divided by 2 is negative 2. A has to be negative 2. Favorite decomposition. There is here constants. So we now have our decomposition.
Yeah, it'd be basically 2a minus 7 equals a 3, right?
Right. So then 2a plus 7 is 3, right? So subtract 7. You get 2a is negative 4, and so a is negative 2.
Oh, yeah.
This is the opposite of simplifying. Right? You're given a fraction, you want to you're given some difference of the fraction, you simplify it by finding common denominator. We're undoing that with partial fraction decomposition. The other way you could do it, and I really raised this method. Continue from here by gathering like terms together. So, if we distribute, we get what? X squared minus x there. So look at the x squareds. You get a plus c, right?
How?
Distribute the a through, you get ax squared,
Minus ax.
and then cx squared here. X squared is common,
So, oh, a plus c x
right?
squared.
So it'd be a plus c times x squared.
Okay, but then you still have to.
Right, so I'm going to do the x next.
Okay.
So now we look at the coefficient for x. Negative a plus b, right? And then look at the constant term. Just negative b. Okay, that way. Then you do what's known as what's called coefficient comparison. Right-hand side, the coefficient of x squared is a plus c. Look on the left-hand side. What is the coefficient of x squared?
Isn't that still a plus c?
Left-hand side.
Oh, the coefficient of x squared.
So what's its coefficient?
0?
Yep.
Okay.
A plus c has to equal 0.
Okay.
Now do the same thing for every single term. X, coefficient on the right, has to equal coefficient on the left. What's the coefficient of x on the left-hand side?
1.
Right-hand side, our constant. What's the constant on the left?
1.
There's your system of equations. You get a linear system, in this case, 3 equations and 3 unknowns. Then you solve it. This one is easy to solve. They already give you negative b is 1, so b has to be minus 1. Negative a minus 1 is 1. Negative a is 2. A is negative 2. Negative 2 plus c has to be 0. C is 2. Oh, that's exactly what we got over here. Either method is fine. That method will always work. This method, while technically will always work, it's going to be a lot harder. Like you can't isolate a lot of your constants. It's a lot harder. So I typically just default to coefficient comparison. Either way, we now have our decomposition. So it's x minus, now remember, it's minus the entire quantity. Negative 2 over x. So this becomes plus 2 over x. Minus 1 over x squared. So that becomes plus 1 over x squared. 2 over x minus 1. There's our integral. That integral can now be done. Antiderivative of x is x squared over 2. What is the antiderivative of 2 over x?
Or 2ln x.
2ln absolute value of x. Antiderivative of 1 over x squared.
X to the negative 2. So the antiderivative would be
X minus 1 over minus 1.
Antiderivative of 2 over x minus 1. Two log absolute value of x minus 1, right? So you saw. We can also simplify that. Right, so combine your two fractions.
How did you get that?
X squared over 2 minus 1 over x. Common denominator is 2x.
Okay.
Both logs have the same coefficient. Which makes it very easy for me to combine them into one log. So that could also be a way to write the antiderivative.
Wait, how does x squared minus 1 over x become x cubed minus 2 over x?
It's x squared over 2 minus 1 over x.
Oh, so it would be x squared minus 1 over 2 x, actually?
So, oh, right. Yeah, that should be a 2 there, sorry.
Okay. Oh, wait, where's the extra x? How did x cubed become x squared?
Because I have to multiply this by an x, don't I?
On the bottom, but half the one on the top.
So you can't just multiply by 1 over x. It's x over x you have to multiply by, right?
Like common denominator.
Right, you only have to multiply by 1. So if I multiply the denominator by x, I also have to multiply the numerator by x.
Oh,
So
so
that's where the x cubed comes from.
okay, so you multiply x squared over 2 by x.
By x over x.
So so then it became x cubed.
Yes. Over 2x. And then this gets multiplied by 2 over 2.
Okay, that's it.
So there's our antiderivative. Again. Give your confidence. Everything else is algebra. Of all the techniques of integration, this is the most algebra heavy. Oh, look, they were nice and they gave you the denominator already factored. Show of hands, who thinks I'm that nice on the test? Perfect, because I'm not. But I'm not so evil that I'll give you like a 5th degree polynomial that you're able to factor that by hand. And yes, I am testing on you being able to do a partial fraction decomposition as well. That is sadly not covered in pre-calc, because pre-calc is only 1 semester instead of 2. Should be 2 semesters. So really get you ready. So no, you can't use a CAS to do partial fraction decomposition. Because I can in mathematics just put in a fractional function, say, give me its decomposition. Which saves a lot of time in differential equations when I have to use it. Is that proper?
Yes.
Yes. What's the degree of the denominator?
X squared.
Well, that's not the degree.
Oh.
That's the lead.
Leading coefficient.
That's the leading term.
Oh, the degree is 2?
So the degree is 2.
Okay.
Degree of the numerator is 1. Perfect.
Yeah.
So we don't need to do long division.
Right.
That's nice. It's already completely factored, so we don't need to worry about that. The first factor is x plus 2. What does that give us to the partial fraction decomposition? What does x plus 2 contribute to the decomposition? It's linear, right? Is it repeated? Was it raised to a power?
No.
So it gives us one term.
Oh, okay.
Something over x plus 2, right? What about x plus 3?
That would be
B
over x plus 3.
Solve for A and B.
There's no c.
There's only two factors, right?
Oh, and there's one for each of them. Okay.
Unless it's to a power,
Okay.
right? So if this was like to the 8th power, you technically have 8 x plus 2s.
Okay.
So that would give you 8 terms. Multiplied by the denominator. And this is extremely easy to do with substitution. You plug in x equals -3. That goes to 0. That's -1, right? Negative b equals -3. And so let's just get rid of those negatives. B is 3. We now plug in x equals -2. B goes to 0. Or what you're multiplying b by goes to 0. -2 plus 3 is 1. So A has to be -2.
Yeah.
So that is what we're trying to find the antiderivative of. That antiderivative is 3 log of absolute x plus 3. This antiderivative, -2 log of absolute x plus 2. There's the antiderivative. You can write that as a single log, but it's going to look hideous. It would be that.
Would it be wrong if we left it the other way?
Nope.
Okay.
That's actually how I would leave it.
Okay.
It just looks cleaner. The other one, since the logs have the same coefficient, it looked cleaner for me to write them as a single log. Here, the logs have different coefficients, so it's not as clean. So write them as that single log. Right, because your numerator and denominator are going to have different powers. here. Is this proper?
Yeah,
What's the degree of the denominator?
3, I think, yeah,
Degree of the numerator?
2.
And look, they gave it to you already factored in. It's almost as if I don't want to waste time in class trying to factor it. We don't have to do any long division. We don't have to do any factoring. What's our first factor?
X
What does it contribute to the decomposition?
would be A over X.
What is the second factor?
X plus 2.
What does it contribute?
B over X plus 2.
What's the third factor?
X minus 1.
So what do we get? What does it contribute?
C over X minus 1.
And there's no other factors.
Alright.
There's the form of our decomposition. Solve for A, B, and C. Again, this is going to be an easy one to do with substitution. No. Yes.
I don't get those.
So remember, we're multiplying both sides through by the denominator. So this is getting multiplied by this. The x's drop out, it's left with their product, right?
A over X would be multiplied by
Yes.
X.
So every single term in this equation gets multiplied by x times x plus 2 times x minus 1. We're clearing out the denominator.
Okay.
If you let x equal 0, you can solve for a. So negative 2a has to be 2. So a is minus 1. Let x be negative 2. That'll let us solve for b. 6 is 3b. So b is 2. Now let x be 1. That'll let us solve for that c. 3 is equal to 3c. So that makes c equal to 1. So we get antiderivative. There's our decomposition, there's our new antiderivative.
So because these are all fractions, they tend to all end up being the natural logs,
Not necessarily.
at least the ones we've done so far.
First one, we got one that wasn't a natural log,
Oh,
because we had 1 over x squared.
oh, yeah, okay. That was like a negative five or something.
But if you get, I mean, chances are you're going to get you're going to get at least 1 natural log out of this method. 9 times out of 10. Leave it like that. I could combine those 2 logs because they have the same coefficient. But why do that and leave this log y? Not combine that, and that has a power. Nope, just gonna leave it like that. And then be bothered by the fact that I decided to do that after I wrote it. Now I have a negative outcome. Not happy about that, but $7 and somehow still functional. It's 4 o'clock. Alright, so just heads up, I don't know when I'm going to get this evening's video rendered. Because obviously when I go home tonight, I'm just going to absolutely crash. And I'm going to go to the hospital with my daughter, and you know how hospital Wi-Fi is. So, don't know if it's going to be rendered tomorrow. We'll see. Your quizzes should be graded tomorrow, though. So keep your eyes on Teams. I should get those grades posted tomorrow. Unless something. Oh, I was pissed. Brought her out of surgery. She's already got a frown on her face, and she's not even actually fully awake yet. So giving people the death looks in her sleep. So you don't see me next week, she killed me. Is this proper?
Yeah.
Yes. First factor. That's what's going to trigger you guys. Second factor.
It's going to be BC and B over x plus 1, x minus 1, plus a C over x minus 1, and a d over x minus 1?
This?
Yes. Close. Or is it just d1, d2, d3 or something like
Well, that doesn't matter.
Okay,
B1, B2, B3, and BCD would be the same thing.
okay.
Would the x plus 1 under c be squared and the x, I'm sorry, the x minus 1 and then the x minus 1 under d be cubed?
Doesn't have to be in that order, but yes, one of them has to be squared, one has to be cubed. There's the composition. There's the decomposition form. Now we can solve for A, B, C, and D. And substitution is not going to be nice in this one. Clear out denominators, that's what you're going to get. Now, I'm technically making a sin here. I should not be using capital D here. Technically, this says the derivative of x plus 2. Capital D is derivative. Okay. This is calc 2, not chemical equations, so that calculates actually means. I don't like using lowercase letters for this, and I don't want to skip D with E because I'm not really confusing. Typically why you'll see A1, A2, A3, A4. But then I have to write subscripts. We can get A very easily, right? By setting x equal to -2. That would give us A. However, we can also get D easily by setting x equal to 1. But you will not be able to get B and C that way. So then you'd have to pick two different values of x, and you can get a system of linear equations to solve for B and C. You know, bloody solve a system of linear equations anyway, I imagine myself a system. We're going to collect like terms, set up a system of 4 equations and 4 unknowns. And if I remember correctly, this system actually turned out to be pretty nice. So that means the first thing that we're going to have to do is expand out the x minus 1 cubed and the x minus 1 squared. Then we'll have to distribute x plus 2 through that, distribute x plus 2 through the x minus 1, and then we can easily collect like terms. Oh, but I taught you Pascal's triangle, which you weren't here for when I did that in Calc 2. I did that last week. But that's okay, because you're in my pre-Calc Calc 1, and I did both of those courses. So I was sad because I wanted to call on you and be like, oh, so how do we easily expand this?
Yeah.
Pascal's triangle. See, it's obvious. Everyone knows Pascal's triangle. X cubed minus 3x squared plus 3x minus 1. There's x minus 1 cubed. There's x minus 1 squared. can do that first term. Now I can distribute the x plus 2 through. X cubed minus 2x squared plus 2x squared. Yay, good one. Plus x minus 4x, so minus 3x, and then plus 2. Do that right. Yes, I did. Perfect. FOIL this out. X squared minus x plus 2x plus x minus 2. Right, and then that d stays the same. Collect like terms. Okay, so that's it for x cubed. X squared minus 3a plus c. A minus 3b plus c plus d x. And what? Minus a plus 2b minus 2c plus 2b. Oh dear. Okay, that system's not as nice as I thought it was. We look at coefficients for x cubed. A plus b equals what? What was it?
I mean, is that something to do with the x cubed plus 1?
That's something to do with it.
1.
Just equals 1.
Were we setting the one side to 0?
I'm doing coefficient comparison. So coefficients of x cubed. A plus b has to equal 1.
Oh, that's equal to coefficient up there. Okay.
X squared, negative 3a plus c has to equal
0.
for the x, 3a minus 3b plus c plus d has to equal what?
0 also.
And then finally, negative a plus 2b minus 2c plus 2d has to equal There's that system of 4 equations and 4 unknowns. Right? So you go to Wolfram Cloud. Right, you've created your free account, so you sign in. You're going to create a new notebook. I'm going to just go ahead and put it at 200% magnification just so it's easy to see on the screen. I think 200% is fine. I might have to go to 300. We'll see. We're solving a system. Right. So the system, or the command rather, is solve. Is that big enough? Brackets. Now we type in the first equation of the system. Now I happen to know for a fact that I cannot use capital D in that because that is the derivative command. It is a saved command.
Are we going to E or something?
I can use lowercase d, so I'm just going to use lowercase letters instead when I type it in. And you'll see, right? If I type in D, you should see it's blue. If I type in capital D, you should see it's black. Black text means the stored command. First equation of the system, A plus B equals 1. You want to do a double equal. Single equal in Mathematica is storing. A double equal is a test. Double ampersand. Second equation in the system. Double ampersand. And you do this for each equation in the system. Uh-oh. Plus C plus D. That's equals 0. And finally, so once you have your system written out,
You know, close the bracket.
comma. Oops, enter, I did not want to do that, it's fine. In braces, what are we solving for? A, B, C. And you should notice that they've now turned a greenish blue. Right? A, B, C, and D were blue. Now they're green blue because I'm saying that's what I'm solving for. Those are my unknowns. Otherwise, you're going to treat anything that's blue as just some value that you didn't. Right? So just some that you're not solving for. It will solve for everything in terms of that. Close out the braces, close out the bracket. When you want to execute Right, so if I just hit enter, it's going to take me down to the next line. To actually execute it, shift, enter. And there's the solution. Now, I personally do not like that form. I just don't like the way it looks. So there is an option I can do. If I come back up here, if I do // and type in table form, capital T, capital F, it'll give it to me without the braces and without the commas. What table form is nice is if you have multiple solutions, it'll actually list them down as a table and not in nasty looking braces that are hard to read. There's our solution.
So are we supposed to do that on a test if we get one of those?
You can.
Okay,
You can also do it on the calculator, by the way.
okay.
So let me show you that. By the way, I'm also recording my screen. So I'll try to line up the screen recording with camcorder recording when I render the video. So you should be able to see both. If I can't get it to line up nicely, then I'll just break it. When I mark on the screen, I'll just insert that portion and looking at the board. I'll figure something out. Okay. On the TI Inspire, you're going to go to the menu, algebra, solve systems of equation, solve system of linear equations. You tell how many variables. So we have 4. What are the variables?
A, B, C, and D.
Now, the calculator doesn't distinguish between lowercase and uppercase letters. So if I were to type that as all capitals, it would still interpret them as lowercase. Which is a shame. Okay. And then you just enter equations. With single equals though. All right, so I'm just going to do the first one, just so you see. It would be what? A plus B, and then here's the equals 1. Down arrow, take it to the next one, and you do that for all of them, then you just hit enter, and it'll give you the solution. So in class, so the midterm and final, well, you have to use it, you're not allowed to use your computer, you're not allowed to use a calculator to type solve the system on a calculator. But remember, exams 1 and 3 are take home. So you can use Open Cloud, and some of the problems are probably going to require you to use it and include a printout of your code. Good? All right, so let me minimize that so I can look at this again. A is 7/27. So 7/27 over, what was it, x plus 2? Then B is 20/27. Over x minus 1. And yeah, a lot of the systems do give you fractions as solutions. Plus 7/9. That was x minus 1 squared. and then plus 2/3 x minus 1 cubed dx.
Now, you said before that, I think it was the order didn't matter which one you did, x minus 1, x minus 2. So if you had 7/9 x minus 1 and 20 over 27 over x
You
minus
wouldn't.
1 squared,
You wouldn't,
oh,
right? So if you wrote x minus 1 squared first, you have b over x minus 1 squared, your b would be 7/9.
oh, so okay, they still have to match.
So no matter what order you do it in, you're still going to get the exact same decomposition, no matter how you write this.
Okay.
Right? So if you write it a different way, you'll get different values for A, B, C, and D, but they're still going to line up exactly like this. Right? Because your A is going to be different than my A if you write it differently.
Okay.
Does that make sense?
Yeah.
So that's why I said the order of how you write this doesn't matter, because you're still going to get the exact same solution. Now, the first antiderivative. Second antiderivative also involves log, right? These two will not be logs because they're not first powers. So this one is what? Power 2, right?
Yeah.
Derivative is 1, so we can just treat this as like u and not change anything. So it's going to be minus 7 over 9 times x minus 1. Right? This antiderivative is negative 1 over x minus 1. Right? Antiderivative of u to the minus 2.
Okay.
Minus u to the minus 1. Minus 1/3, right? Because I'm going to be dividing by a negative 2. 2 over negative 2 is minus 1. So minus 1 over 3 times x minus 1 squared plus c.
So if you have a fraction up there, you're doing the derivative, you're going to be like the numerator of the fraction divided by the denominator of the fraction times whatever's in the original denominator, but with the power reduced by 1.
Hmm.
It kind of looks like.
So there's a reason I wrote it. There's a reason why I write the fractions in the numerator, because these are the constants.
Yeah.
So really just ignore the constants, say what is that antiderivative? Negative 1 to the, or negative 1 over u.
Yeah.
Now multiply that by 7 times. That's what I'm doing.
Okay.
Same thing here. U to the minus 3, antiderivative. So I agree there's a u squared in the denominator. But the power is minus 2, right?
Yeah.
So you have to divide by that. So negative a half u to the minus 2.
Okay. Yeah.
Right? Now times that by 2/3.
Okay.
If you want to solve that by hand, that's fine. Method of elimination, remember that? From algebra.
Okay, you solve 2 of them and then try to use those to solve.
Well, no, you have to actually eliminate all but 1. And then do that substitution. It's a pain in the rear end. Again, that's something that is actually in pre-calculus textbooks. They just don't cover it because we don't have this should be a 2-semester course. There's a lot of stuff that you cover in pre-calculus, that we marry for calc.
But there would be a way to do that, because I know we were able,
Yeah, there's a way to do it. It's method of elimination.
right, I mean, but there's a way to actually eliminate all but one, because I know
Yep.
we could do two of them, but,
Yep. And this one you can.
okay.
I know you can because you get one unique solution. You can't always. That would be either no solution or an infinite number of solutions.
Okay.
But because we're doing partial fraction decomposition, you're always guaranteed a unique solution if you set up your system correctly. So I probably don't have time to get through one more. What we do. What we do on Monday is actually simple. So if I have time, I'll come back to the last problem. I is this proper?
It is.
The denominator is not fully factored. So we have to factor it. But that's okay. Because this is quadratic form.
So, I get it.
Factors of 2 and added give you 3. 2 and 1. Yeah, sure. Factor. X squared plus 1 times x squared plus 2. Is this fully factored?
Yes.
Right. Neither of these can be factored any further. They're both irreducible quadratics. What is the first factor?
A over x squared.
not linear.
Oh.
It's irreducible quadratic.
Oh. That's gonna be different.
And so the first factor is x squared plus 1, right? It will give you ax plus b over x squared plus 1. So what does the second factor give? What is it going to contribute to our decomposition? Well, I wouldn't use A and B in this case.
Are we maybe just gonna do cx plus b or something?
That works. Over what?
Over x squared plus b.
Now we do the same thing. Clear the fractions. Right, so multiply everything through by x squared plus 1 times x squared plus 2. Yeah, I'm going to go ahead and FOIL instead of trying to do it in my head. Ax cubed plus bx squared plus 2ax plus 2b, so that should be that first term, FOILed, plus cx cubed plus dx squared plus cx plus d. For x cubed, you should get a plus c. For x squared, b plus d. For x, 2a plus c. And then the constant, 2b plus d. What does a plus c have to equal?
1.
What about b plus d?
1.
2a plus c,
1.
2b plus d.
2.
Notice how I wrote it. I wrote it this way for a reason. Technically, we have a system of 4 equations and 4 unknowns. However, notice that 2 equations contain only a and c. The other 2 equations only contain b and d. So you can actually break this down into 2 systems of 2 equations and 2 unknowns and solve each system individually. which makes this easier to do by hand. -1, so I'm going to multiply this entire equation by -1, and then add the 2. -a plus 2a is a. -c plus c is 0. -1 plus 1 is 0. A equals 0, which means c is 1. That's the method of elimination. Obviously, it's more complicated if you have more equations and more unknowns. Same coefficients, so I can do the exact same step. Multiply first equation by -1 and then add it to the second equation. B is equal to -1 plus 2 is 1. B is 1, which means D has to be 0. Right? All I did was I took B equals 1 and plugged it into the first equation. You can plug it into either equation, and then that lets you solve it. There's our solution. A is 0, B is 1, C is 1, D is 0. So our antiderivative now becomes 1 over x squared plus 1 plus x over x squared plus 2. What's the antiderivative of 1 over x squared plus 1?
Natural log? No. Oh, yeah.
You should definitely know it.
Yeah. Let's talk about it.
A lot of people don't cover this in Calc 1 for some reason. I do. So this is a known antiderivative. So again, you want to ask yourself, what function has derivative x squared plus 1? Derivative of what function is 1 over x squared plus 1?
Oh, it's one of the inverses.
It's an inverse trig. Which one?
It's the tangent inverse.
The inverse tangent of x. What is the antiderivative of x over x squared plus 2? Hint, what's the derivative of x squared plus 2?
Oh, the derivative.
It's the derivative of x squared plus 2.
2x.
We have an x. So you saw. let u dx squared plus 2. Du is 2x dx, which means that dx is du over 2. So that's where the 1/2 comes from. And then the derivative, or not derivative, antiderivative of du over u is natural log absolute value of u. So we actually need those absolute values here. Can I just write this in parentheses? X squared plus 2 is always positive, isn't it?
Well, yeah, because x squared is always going to be.
So we can just drop the absolute values in that case. You're not wrong if you include them. They're just redundant. Right, it would be the same thing as if the value is always guaranteed to be negative. I could drop the absolute value by multiplying what's inside by negative. We'll say that. Sorry. So this was the last question that I had for this problem set. Oh, wait a minute. Oh dear, I need to make a correction. Somehow, one of my terms got deleted. Oh, that's easy to fix. It's fixed. So again, if I have time on Monday, we'll come back and look at this one. This was actually really fun, so I would encourage you to try and do it on your own. It looks intimidating, but it actually works out very nicely. So be warned, with method of partial fraction, yes, you can have inverse tangent antiderivative. If you get repeated irreducible quadratic, it could be possible to get something like x over x squared plus 2 squared. Oh no, I'm sorry, not that. Because that would just be yourself. 1 over x squared plus 2 quantity squared. That's true. That you have to use trig sub on. So yeah, you may have to do trig sub as well within the method of partial fraction decomposition. When you do integration by parts, it's possible that you get a trig sub out of it, or you wind up with having to do a partial fraction decomposition as well. Those are the 3 techniques for finding antiderivatives on top of u sub. So integration by parts, trig sub, and partial fraction decomposition. Doing it by hand anyway. There's also ones where you have to do clever substitutions before you can do one of the techniques. I think I will be looking at some of those Monday, some of those clever substitutions. The only technique we have left for antiderivatives is reading a table and using CAS. So that's fairly simple. That's going to be Monday. Then we look at actual intervals. So improper integrals, what is an improper integral, and then how do we numerically evaluate an integral? So, obviously, until you're working on math, at this point, you can work up through assignment 4. As of 7 o'clock this morning, still only 2 of you have done any of the problems. You're running out of time. It's due February 21st. That is, what, 2 weeks away? So you're running out of time. You may want to get on that. Also, a reflection just went up. Now that we covered the 3 techniques of integration by hand, reflect on them. All right, so there are 5 prompts there to respond to. This will be typed up in Word. You'll print out a hard copy and turn it in, what is it, the 14th?
Physical copy?
Yeah, physical copy. And then if you want to be safe, also you can also upload the electronic copy on here, just to be safe. Like say you get sick, if it's uploaded before the deadline, I'll still take the hard copy. Thanks, you at least upload it online. Or let's say you upload it, and you get it done, you upload it, it's pouring ass rain, and it's in your bag and it gets destroyed. The hard copy. At least you have the electronic copy on time, so then I'll take the hard copy with you. And of course, if you want to see how it's going to be graded, we'll look at that for you. So that is due the 14th, which is Valentine's Day. It is. It's next Wednesday. Start of class next Wednesday, so 6 p.m. Have a wonderful weekend. See you again on Monday.